Over to you, Dr. Jaykumar. And most of you know Dr. Jaykumar Vaiti Shankar, so I'm not introducing. He's a PhD and then most of his work has been in quantum computing. Last 5 years, he's actively worked, and he's the CEO of Anutantra. For those who are joining for QT-05, and I think this is his first lecture in this session. And earlier, QT-03, many of the sessions were handled by Dr. Jaykumar. And it's a very happy thing to see. And also he's having the title IBM Educator. He's done the KISS-KIT course, global summer course, and is qualified for that. And is qualified by IBM to be an educator on quantum computing. And he is extensively spoken in last 1 year. I've been following his LinkedIn. So across various institutions, including the prestigious IISc Bangalore, he has conducted workshops. So we are happy and we're privileged that he's here, and over to him for this time. Thank you.
Thank you, Professor. Thank you so much. Good afternoon to all. Happy to join in this wonderful QT-05 lecture series. Is my screen visible, sir?
It's visible.
Yeah, thank you. So once again, I welcome each and every one of you for this lecture series. Before that, yes. So today, the topic is about quantum complexity classes. This is very, very important topic in entire quantum computing. So why we are moving towards quantum is entirely based upon this topic. So many investigation happen so far, happening, and it will happen in future also, because whenever our device is not capable to do something, we are looking for alternative. Okay, so that is why we are looking for quantum computing. Instead, classical computer it has some limitations. So we need to overcome that limitation with new type of device. Okay, so actually it is not device based, it is about the complexity of a problem based. Okay, so whenever our device not able to solve a particular kind of complexity, then we are looking for alternative versions. So this topic is very, very important. We will start with quotes. Okay, so in natural science, nature has given us a world. We are just to discover its law. Okay, so if you want to discover nature, we need to discover law if you want to understand the nature. But in computer, what we can do, we can create laws and we can stuff laws into it, and we are able to create world across it. Okay, that is the beauty of a computer. So in computer, we try to create a world by doing programming. So it gives like godlike power. Okay, so that is why whatever we are able to accomplish in today's scenario, everything is set up by computers and computer algorithm. So most of the time, CS and IT field will dominate each and every field in this entire globe. Nowadays, the boom of AI will proven, boom of quantum will proven it. Okay, very beautiful quote given by Alan. And if you're looking at the second quote, for our field is still in embryonic stage, it is a great that we haven't been around for 2000 years. And we are still at a stage where very, very important results occur in front of us. So exactly whatever the AI, ChatGPT, all this quantum moment is happening, it is happening at very rapid pace. So if you are taking the entire historical timeline, the changes happening within this 100 year or within this 2 decades is very, very rapid, is very, very fast. Okay, in technology ways. So what is the motivation of this lecture? This motivation of this today's 2-hour lecture, there are intrinsically hard problems that today's computer cannot handle. Okay, so that is why we are looking for alternative computing or alternative the way of computing. Okay, so with the help of quantum, we try to figure it out whether it is possible or not. Okay, so to understand this, we need to understand what is the computability theory. So sometimes if we are using computer, we need to use for computation purpose. So the basic behind this computable theory is proposed by mathematicians Gödel, Alan Turing, and Alan Church. And these three concluded some basic problem cannot be solved by computers. Okay, so most of the time what we are teaching, what we are understanding, computers are devices to solve our problem, but some mathematical problem never ever able to solve by computers. Irrespective of your configuration, your computer not able to solve. Okay, so these are the three main mathematical pillars they develop computable theory. Okay. Say, take an example of a simple problem. Determining whether the mathematical statement is true or false, your computer not able to decide by on its own. So whatever the powerful computer we are able to create, the computer cannot decide on its own autonomously. Okay, to take this decision, we need to give some input, we need to give some feedback. So humans can easily do this problem where the device cannot solve this problem. Right? Even though this look very simple, even though the AIML, you need to give some input. So based upon the input, it will take decisions. Right. So what is the basic understanding of this problem? All these kind of problems solved by computers, they strictly lies within the realm of mathematics. Okay, so you need to give some mathematical rule or mathematical law in order to take these decisions. So without input or without this frame of law, computer cannot decide on its own. So in this situation, results in developments of ideas pertaining to theoretical model of computer, which in turn may lead to construction of actual computer. So the evaluation of a physical device came from a mathematical abstractness or theoretical model. Okay, so whatever we got so far, all these computer revolution started from theoretical model. Okay, so as we know, process or set of rules to be followed in calculation or other problem operation, especially by a computer. So your algorithm is the abstract one or virtual one, where computer is a physical device. Okay, so in plain English, nothing more than series of steps that turn some data into more desirable form. So whatever the data we have in input form, your device will process it based upon the rules you designed in the algorithm, the form of algorithm. Your device able to produce answer, solution, all your output data. Right. So if you consider all this stuff, so most of the abstract model you're able to build is Turing machine. So Turing machine is an abstract model of computation where it can perform all this stuff. Okay, so before inventing a device, they formulated the abstract model. So such abstract model is called Turing machine. So if you want to do computability, you need to understand what is the complexity involved in that problem. So I will take some pin over here. So why we go for algorithm? To solve problem. To solve problem, first we need to check whether that problem is computable. The next question we need to ask whether what type of complexity involved within. So we need to ask these basic two questions to solve a problem. To solve a problem. So with the help of complexity theory, what we can do, we able to classify problems as easy one, hard one, where we can able to understand the computability tends to classify problems as solvable, not solvable. So once you identify your problem as easy or hard, then you're able to understand whether it is solvable or not solvable. So if your problem is easy to compute, easy to solve. If your problem classified as hard, it will be very difficult for solving. Okay, sometimes, sorry, most of the times. Okay, so computability theory introduced many concepts used in complexity theory. Take an example of Turing machine. Take an example of Turing machine. It is a powerful model proposed by Alan Turing in 1936. So Alan Turing is very important person in computer science field, where he developed this Turing machine model in order to solve or crack German submarine communication. Okay, during World War I and World War II, Germans are used to build submarine. They will communicate with each other in very secret way. So UK, United Kingdom, British Empire, they need to crack this code. So they invented lot of mathematicians. So one such mathematician is called Alan Turing. So during that time, he proposed Turing machine. Okay, it is the best mathematical model ever built for computability theory. So if you want to compute something, you need to do abstract model before that, right? So it can do whatever a typical computer can do, but it cannot solve some problem that are beyond theoretical limit of computation. So if you have a problem, so you need to logically abstract it, then based upon this, make a theoretical machine. Okay, if this machine able to solve a problem, then you can able to execute in computer. In simple terms, able to execute in any computer. Suppose if this machine not able to solve your problem, you cannot solve in any computer. So this is the conclusion you can get from this model. Okay, so before solving any problem, we need to check whether it is computable or not. If it is computable, you need to classify the degree, easy or hard. Then if you classify it easy or hard, you need to check whether it is solvable or not solvable. If Turing machine not able to solve, you cannot execute in any type of computer, irrespective a small scale computer or supercomputer. So you need to take decision. So after doing all this stuff, is kind of computability theory that investigate power of a given algorithm to solve some problem. So if you devise some algorithm, it should have power to solve that problem, right? So it also necessary to know unsolvability of some problem. So this is very important rather than solving a problem, because some problem, if you are not able to solve, how much you are trying, how long you are executing that problem in your computer, you never get a solution. So for this, what we supposed to do, we need to do reducibility. So reducibility is a primary method of proving that certain problems are computationally unsolvable. So we need to do all these parameter check in order to identify what type of problem we have. Okay, so reduction is a way of converting one problem to another problem in such a way that a solution to second problem can help solving the first problem. So it lies in step by step. You can look like staircase way. Okay, so this is your goal. This is the starting point. So you need to stall step by step. So step 1, if you're able to solve step 1, you are able to solve step 2. Okay, so each and every problem you need to divide in such a way to solve step by step. So for an example, you cannot repair an electrical fan if you don't know about electrical works. So this problem is unsolvable for you because you don't have knowledge about how to repair a fan. Imagine. Suppose if he able to find an electrician, then he can get it repaired. So finding the electrician is the second problem. If you are able to solve the second problem, then you are able to solve the first problem of repairing the electrical fan. This is very good example. Okay, so most of the time in most of the science project, we will divide the solution in step-by-step or procedure. Okay, so if you're able to solve the second problem, you're able to solve first problem. So it contains dependency. So if your problem contains dependency, then you need to solve one by one. So it is like unwinding. So unwinding wire, we need to get all this stuff. So we discussed about computability theory. First, we need to design a Turing machine. So once you design Turing machine, you're able to decide. Once you're able to decide, you need to apply regression theorem, whether your solution is solvable or not. Once you have this theorem, you're able to reduce number of steps. So within this, if anybody have any doubts, you can put in chat box. Is it clear until? Are you able to follow? Am I audible? Yes, thank you.
Yes, sir, you are audible, clear.
Thank you, thank you. So how to identify the given problem is difficult or not? Okay, I will show the previous page. This one. Okay, I will share this slide. Don't worry, just follow. Suppose if your question is given like this. So if you have me, you want to share me. If you share me, you lose me. What am I? Can anybody able to answer this puzzle or riddle? Put in chat box. No, read it once. If you have me, you want to share me. If you share me, you lose me. What I am? Not money. Not money. Happiness, no. Grief, no. No food. Okay. So different answer. Very good. Secret. Great. So this is secret. Okay. If you have secret, you want to share. Once you share, you will lose. Knowledge, you never lose. Always you have knowledge. If you share knowledge, you won't lose it. Okay. So this problem is very, very easy. This problem is very, very easy. So look at the next example. If you want to play Tetris. So how many options are there? So in this diagram, how many options are there to place this particular pattern? 6. So 1, 2, 3, 4, 5, 6. So there are 6 possibilities, probability. All right. You can turn into horizontal also, and you can place. So it becomes multiple. But the best possibility is 6. The best way to place. Otherwise, you can rotate this, and you can place over here also 7. Right. So when compared to this is some more difficult. Some more difficult. So this problem contains only one solution. Only one solution. But this contain many. Whenever you have multiple choice, it becomes much tougher. Okay, sometimes it is easy to do fill in the blanks. Sometimes it will be very difficult to do MCQ. So options will confuse us, right? To solve a numerical problem, to factorize two number, to multiply these two number, so it depends upon the way it is implemented. You can do factorization in multiple ways. You can do multiplication in multiple ways, but the result is same. The result is same, but the way you are doing, right, it will differ. So the solution is here the same, but the way you implement have different options. Take an example of chess. So each and every possibility, if you are changing the state of a coin, the entire game scenario will change into difficult level. Okay, very different level. So much more combination, much more probability, the entire scenario is going to change with each and every step. Okay, so take an example of Sudoku. So here it is similar to chess, but it involves with numerical value also. If you take an example of a row, the row contains only 9 possibilities, 9 possibility of all this number, but each and every cell also contain 9 possibilities. Okay, so if I'm giving this Sudoku for each and every person, they solve in different way. The answer will be the same. The solution will be the same. But each and every person will try to solve in different approach, and each and every person will take different amount of time. Okay, so here the problem is same. The solution is only one, but the way you are doing, the way you are approaching, the way you are feeling is entirely difficult. So entirely different. Take an example of this problem. So count grains of sand in a seashore. So theoretically, so somebody can say it is possible. So theoretically it is possible, but practically impossible. Practically impossible. If someone asks you to do this task, you will ignore, right? If someone asks you to do this remaining 5 tasks, you will do. So before doing any problem, before solving any problem, you need to decide whether that problem is able to solve. If you are able to solve, how much difficulty it is. Okay. So this is very, very important to do any programming or any solution. Suppose how to get a solution. This is your problem. So this is your goal. This is your goal, right? You want to navigate to this point from this source. This source mentioned this is destination. So you might have multiple ways. Either you can go all the way through this sea and you can land over here and you can reach over here, or you can step down at here and you can go through landways. So for the same goal, you have multiple paths. In the same way, if you have system, if you have computer to solve a problem, you need to ask this question first. Does solution exist? If solution exists, try to use it. If solution doesn't exist, then what you need to do, you need to ask this question whether algorithm is there or not. If algorithm is there, try to use it. Otherwise, you ask this question whether this algorithm contains how many steps. Okay, so this question is important because it depends upon the number of steps, it will take time. So you need to ask the subsequent question how long it will take to solve the given problem. So next, what you need to ask, if how long it will require, then you need to ask how much of resource you need to provide for your problem. Okay, so here the resource means your main memory. So normally they will call it as RAM. So next you need to provide the processor capacity. Okay, so next you can mention time also, how much time it will require. So normally you can categorize all these programs, all these resource in the terms of time and space. Suppose if you are able to solve a particular problem, then you need to ask whether that program eventually stops or not. So if your program is unstoppable, it will form into infinite loop. It won't exit. Okay, if it won't exit, you don't know what is the solution you processed, what is the solution you got. So all these questions are important. Then finally you need to ask this question whether the solution is efficient or not. So how will you calculate your solution is efficient or not? Based upon these two parameters. So how much time it took and how much space you require to provide all your computational resources. Okay, so the difficulty of your problem involved with too many steps. So if you are a algorithm designer, what you need to do, you need to count each and every step, each and every line in your program or algorithm. Suppose the given task is to bake a cake with the given ingredients. So yeah, making a simple cake with 2 or 3 ingredients is very, very easy. Very, very easy. Quickly you can do. But if it requires additional steps, take an example of adding 12 ingredients. Suddenly this task become little difficult. So creating a cake with 2 or 3 ingredients is very easy. But if you increase ingredients, the same task will appear difficult. Okay. So take an example of multiplying numbers. If the given number is 3, it is very easy for you. But if we increase the number of inputs up to 100 numbers, the same task will appear so difficult. Okay. Take an example of sorting books by title. A given pile of books in your disk. If you have only 10 books or 4 books in your disk, it is very, very easy to organize. But if I'm giving the entire library of books, the task become apparently very, very difficult. So you need huge amount of manpower and you require 1 or 2 months to do the same task. The task is same, but if you increase the number of inputs, it become almost untangible. So take an example of Rubik cube. 2 cross 2 is very easy, but if I give 8 cross 8, even though the experts, they will struggle. Okay, so you need to ask this question on solving problem. What are the questions you need to ask if it is very, very difficult? Okay, so this will help you to solve very, very difficult problem in your domain. Take an example of trial and error. Suppose if you have the problem, that problem contains multiple solutions. Okay, take an example of the suitcase. So if you are very good at remembering your keywords, you are easily able to open this suitcase. Suppose if you forgot or you took suitcase from your friend, but you don't know what is the passcode, then what you will do, you will do trial and error. Each and every time you will do trial and error. So it will take some time. At one combination, you are able to crack. Okay. So if you don't know solution, you need to do multiple trials. So based upon the error, again, you need to do computation. You need to do trial. Okay. Take an example of finding a needle in a box. Very, very easy. But if I'm giving a very big haystack, so finding needle in this haystack is very, very difficult. Okay. So what technique you are able to use? You can use magnet. And you need to scan each and every part of your haystack. At one point of time, you will to get, but the same problem becomes very difficult because you don't know where it is exactly located. Right. So take an example of finding prime numbers of 91. It is very easy, but if I gave 4-digit number, the same task apparently become difficult for you. So I can give multiple examples like this. The another problem with computer or any device, difficulty with memory. So take an example of our day-to-day life. Suppose if I am giving this pattern. So if I am giving this pattern, I need to find the matching pairs. So what I do, I will show what are the matching pairs over here, and you need to observe, you need to tell the answer. How many matching pairs are there? Exactly. So two matching pairs are there. You can see over here. So this is one pair and this is one more pair. So two pair. Suppose if I am displaying 15 pairs, it will be very difficult for you because our brain have limited capacity. It will focus only for the important problems. Okay. At the same time, it cannot focus for 15 different inputs. Okay. So keeping something in memory for shopping list of 3 items is very, very easy. So if you want to retain 500 items, you need to prepare a list. You cannot go for shopping with the 500 items in your memory. Okay. So this type of difficulty you will get while solving a problem. Okay. The one more important difficulty, difficulty of options. So this is much more confusing. Suppose if you have a jigsaw or puzzle, okay, you need to start from here. You need to start from here. It is your ultimate goal. It is your ultimate goal or target. Okay. Suppose if you try to find a way which will lead to intermediate result. So this is intermediate result. You can say result 1. Okay, orange juice. Otherwise, if you go in another way, you'll get a bug. So this is result 2. Okay. So suppose if your problem have multiple solutions, if your problem has multiple solution, then you need to optimize. So landing result 1 is better while landing result 2. So this is a bug. Consider this is a bug. Okay. Even though you are not able to achieve your ultimate goal or target, if you land on result 1, that is good enough. So always there is a saying, if you have multiple options, okay, much more confusion. Okay. Because you can take any choice, but you don't know which one is the best. At least you need to look for better option from comparing one to another. Okay. All our short-term goals are looking like intermediate results. I'll skip this slide because it will take some time. Okay. So if you want to crack a password, so we can discuss the complexity through easiest problem where everyone can understand. Okay. Take an example of username and password. So here, normally the passwords are 8-bit characters. 8-bit characters. Okay. So if you want to crack a password or break a password, what you need to do, you need to count how many keyboard characters are available in your keyboard. Okay. So there are totally 85 key characters available. And what is the password length given? It is 8. For each and every character, you need to use 85 possibilities. So if you compute in such a way, so 85 to the power 8, you will get nearly these many options. So nobody in this world is able to crack password. Okay. So that is why the much more combination and permutation will increase complexity of your problem. So here cracking password is the problem. Okay. The problem is happened due to much more combination and probability. Right. So this will create complexity. So this complexity is good for secure your password. Secure your password. So each and every character set. Suppose if you are using a small letter A to Z 26, capital letter A to Z 26. So 26 multiplied with 26 and your numerical digit 10. If you multiply all these together, then you can try for a single character. Okay. So sometimes the difficulty of your problem will give solution for some other problem. Our password itself is very difficult, right? So how does your problem grows? So if you want to understand this, we need to take tour of computational complexity. So now we are entering to our given topic. This topic is a little difficult from non-computer science background, right? So for this, Alan Turing came up with a model of computation that we still use today. It consists of a infinitely long tape, some instructions and mission state that reads and writes symbols on the tape. For simplicity, I'll show this diagram. So this tape is infinite in length. So it is imaginary. So no real system have infinite amount of memory. Okay, it is imaginary model. Okay, so here it contains instructions, or you can say mission states. So this mission state you can consider like input and output. Okay, and it will able to do read and write. It able to do read and write. Okay, so your data contains both instructions. So according to the instruction, this model will perform all its operation. We'll discuss later. Okay, so if you design this Turing model to solve your problem, anything a modern computer can do, a Turing machine can do. Anything a Turing machine can do, your modern computer can do. So it is vice versa. If your Turing machine cannot do, your computer cannot do. If your computer cannot do, you are not able to create model by using Turing machine. So understanding Turing machine will give a deep insight what is the capacity of your device. Okay, so it is able to lead a famous church Turing thesis. So if you got time, go and refer this church Turing thesis, right? So they developed one model which is called church Turing thesis on based upon some Turing test. They call Turing test. So in Turing test, what they will do, they have a wall. They have a wall. Okay, you cannot see what is um, this side of this wall contains, and it is divided into two categories. So one side they had human, and one side they have computer. So if you are giving problem, okay, to both human and computer, and this side we have examiner, and this side we have examiner. Maybe I will, here is some content. So what examiner will do? Examiner will give question to a computer and a human. Okay, and both will give result. Both will give output result. Maybe I will differentiate the color. So this result is given by computer in green, and this result is given by human. Okay, if examiner not able to differentiate the result given by a human and result produced by a computer, then your machine is said to be passed Turing test. Passed Turing test. It means your device is intelligent enough. So this is a hypothetical theoretical model to check whether the computer is intelligent enough or not. Okay. So how to measure algorithm efficiency? So obviously, so if your algorithm need to do all this process step by step in fewer steps. So fewer steps. So if you do so, then your algorithm is said to be more efficient. Suppose if your algorithm taking multiple steps, not like linear, it will take so many steps. Okay. So this is what happens in reality. But even though it need to run faster, it need to use less resource. So this is ideal case, which never going to happen. This is in reality. Even though in reality, it need to take as much as less step, and it need to run fast, and it need to use less resource. If your algorithm satisfy these two criteria, then you can say your algorithm is efficient. Suppose if you want to measure the efficiency, it is not independent of your hardware or your implementation. So most of the time, what we'll think, suppose if you have faster computer or faster laptop or supercomputer, our problems are get solved. So normally for day-to-day life problem, it will be easy. So if you have higher capacity device, it will solve in short amount of time. But if you go in R&D level, if you go in most complex problem, it will not happen, right? So efficiency exactly depends upon the input size. So you need to investigate. If you increase input size of your problem, then you need to understand how your algorithm works. Okay, so this question is important. When input size grows, what happens to your algorithm and how much runtime it will get slower, right? So this analysis is called time complexity measure. So you need to understand both how much time it will take and how much memory space you need to allocate. So these are two important questions you need to ask, whether if you design an algorithm in efficient way or not. Okay. So what are the computational resources you're using for your algorithm? It will fuel, okay, your time, your space, randomness, right? Your communication, your quantum physics and parallelism. So today's topic, we covered the time and space, and we never covered randomness, and communication it can taken place in classical also. So these three belongs to classical. Okay. So these three belongs to quantum. So you can see a division over here. Sometimes you can create randomness in classical, that is pseudo random. Suppose if you want to create some randomness using program, it is always said to be pseudo random. So until this, if you have any doubt, you can put in chat box. I will wait. Any doubt until this? Is it clear? Shall we proceed? Okay, thank you. You can proceed. I will elaborate quantum example. I will come. So take an example of polynomial time. A problem in the class P, if the running time of the best algorithm grows as the power of the input size. Suppose if your input size is n, if you exponentially raise it, so n to the power 0, n to the power 1, if you keep on increase, then that problem is belongs to class P. So these class P problems are solved in achievable or reasonable amount of time. So you can solve that problem and you are able to verify that problem, right? So the task, just like your desktop or a smartphone can do, are in P, such as finding routes, searching your files, or playing games. So all these tasks are belongs to class P problems. Take an example of arithmetic operation, multiplication, or sorting a given list, or solving a simple Rubik cube. So this is simple. So I need to mention. Make an example of 4 cross 4 or 6 cross 6, right? So these types of problems are polynomial. Suppose if you have non-deterministic polynomial time, which is the classification of NP short form. Okay. So what this problem will contain? So these problems appears much harder than P and taking far longer to solve. Take an example of a problem in class NP when its solution can be easily checked. So there are two criteria. If your problem is NP, if your problem is NP, you cannot solve in polynomial time. But you can verify its answer or solution in polynomial time. So this is the clear difference between solving your problem in polynomial time and checking your solution in polynomial time. So for class P, you're able to solve and able to verify your answer within polynomial time. But in NP, you cannot solve in polynomial time. But once you solve, you can verify. Okay. So there are a lot of examples for this. Okay. Take an example of factorizing a number. So you cannot guarantee at what time you are able to solve this problem. If input size is small, it is very easy for you. But if I keep on increase the input size, you cannot say at what point you are able to factorize the given number. Okay. So take an example of packing a suitcase. So you have n number of clothes and you need to pack in the suitcase. Each and every person will pack in different way. And you cannot say which one is most efficient. For some person, a small suitcase is good enough to put all their luggages. For some person, they don't know how to pack, so they require extra more luggages. So it depends upon how we are packing, right? So lot of possibility, lot of combination, lot of solutions. Same way, if you try to solve a Sudoku, you don't know when you're going to solve, but once you solve, it is very easy. Once all these details are given, you can easily verify. Same case to this. Once the suitcase is fully packed, you can say whether the package is efficient or not, right? So checking is always easy, but doing is somewhat tough. Okay. The next category is not polynomial time. So unsurprisingly, there are also problems that can be neither solved or not verified in polynomial time. So which one is true? Yes. Which one is true? Okay. Okay, some problems are not able to solve, not able to verify its answer. Okay, take an example of Go game. So today you go and check the structure of Go game exactly to chess. They are playing in Japan and China, right? So these two games are much more harder. Okay, you don't know when the game going to finish, and very difficult to check its solution also if it is in intermediate level. So final solution we able to know, but intermediate level we cannot verify. Okay. So take an example of this website, Complexity Zoo, where you can see all types of complexity of entire algorithm. Okay. So they have very good encyclopedia about algorithm complexity. So it is created in Waterloo University, located in Canada. So take a look about this website. If you are interested in theoretical mathematics or theoretical computer science, you can visit this website. Okay, so take an example of polynomial time problem versus NP problem. Okay, so class P problems efficiently solve problems, where in case of NP, it is efficiently verifiable problems. Okay, so you can consider like this. So class P belongs to NP category. So NP will act like superset, where P act like subset of NP. Okay, so whenever if you are classifying your algorithm, you need to classify by using set theory. So which one is more complex, which one is more easy, you need to classify in such a way. And this is very important question, whether class P equal to NP can be efficiently verified problem be efficiently solved too. It is debatable. You cannot say in such a way. Okay. So if your problem is P, it also belongs to NP category, but it is not reverse. Sorry, I put in two-way arrow mark. So if your problem belongs to P, it is also belongs to NP. But if problem belongs to NP, it is not belongs to P. Okay, so if you categorize in set theory, it is very easy for you where it belongs to, right? So this is arguable. So many debates are going. It is believed that P is not equal to NP, but there is no proof. Same way, there is no proof for P equal to NP also. So if you are able to solve this problem, if you are able to solve this major unsolved problem in computer science or mathematics, they're ready to offer $1 million. So go and check this website, playmath.org. Okay, they put this problem in very beautiful explanation. So try to take a look in this website if time permits. So if P equal to NP, suppose if you are considering class P problem equal to NP, it greatly increases the slope of what we can know and discover. Okay, mostly you can break cryptography. So this is what happens. They implemented the same kind of scenario in quantum. In quantum, what happens? The NP problem appeared to be class P problem only in quantum. Only in quantum. Can anybody able to say how RSA algorithm or RSA cryptography is cracked in quantum? Using Shor's algorithm. Okay. In Shor's algorithm, what we are using, we used factorization. So this factorization done by quantum Fourier transform. So it able to check those problem as per periodicity. If you use that technique, the problem NP looked like polynomial time problem in quantum category because so much of randomness. Okay, so much of randomness. There is no strict evidence to prove it. So much of randomness involved. So for quantum computer, whatever you classically classified as NP, it appears to be P. Yes, sir. I will take 5 minutes break. So time is about. Yes, I'll take break. So we'll take 5 minutes break. Then we can rejoin at 3 o'clock.